functions, because when we say AND gate, we'll probably be talking about the electronic device itself, but this is not the case here. We are talking about the function. So the AND function, as we all know by now, simply means that for the output to be a logic high, all the inputs must also be a logic high. That's basically the description of an AND gate, that for the output to be logic 1, all the inputs must be logic 1. If any of the inputs is a logic 0, then the output will just be a logic 0. And that is what I gave out in terms of a ladder diagram, because we said that our ladder diagrams are based on expressions such as if A, then Y. That is, if an input is of a certain binary state, then the output is also affected based on the function. So in our case here, we are dealing with an AND function. So therefore, this is the critical function that determines what the output is. And the inputs A and B can take any states 0, 0, 0, 1, 1, 0, and 1, 1. But the key is if the input A is 1 and the input B is 1, then the output Y is 1. Because we were talking about if A and B, then we get an output of Y. So because it is an AND function, we know that the only way to have the output be expressed as a logic 1 or logic high or a logic true, then both inputs must also be high. I hope that is clear. So I'll not dwell on that too much. I want to move on to the next function, and we're going to make them complex as we go along. Okay. So the next one is basically the OR function. The OR function. And we'll try and use this in several applications also as we study. Okay. Now, in an exam setting, it is very difficult, and the reason why I'm drawing this in different colors is simply to illustrate to you, especially when you interact with these ladder diagrams in your softwares. But in an exam setting, it's very difficult to draw different colors for the inputs and even the output. Okay. But here it is simply for illustration purposes so that we understand how they work. Okay, so let's go to the OR function. So how do we express, let me just say, ladder logic OR function? We are looking for a ladder logic OR function. This is the next one. Now, again, the best way is to understand that the OR function also examines the different inputs and then provides one resulting output. Something I forgot to mention even with this is that they don't have to have only two inputs. These AND gates could have more than two inputs. They could have 3 inputs, they could have 4 inputs, but we still know that the relationship between the inputs and the outputs remain the same. That the logic state for the output will only be a logic high if all inputs, however many they are, if all inputs are high. The same way with the logic OR, that the relationship that the logic function has with the output is such that it will examine all the inputs of the OR function and provide an output based on the OR expression. Okay, so this is exactly what we want to check right now. So if we start with a ladder diagram, so we will stick to the 2 inputs, but the inputs can be more than 1. Okay, so let's stick with the 2 inputs and we have an output here. Let me use 0, 0 could be termed as false, false. 0, 1 could be false, true. False, true. 0, is it 1, 0, true, false, true, false, and then true, 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 to mean 1, 1. Okay. Now the output Y. So the inputs are, let me just say the inputs are A and B. The inputs are A and B, and the output here is Y. Okay, the output there is Y. So now, for an OR gate, the relationship is as long as any of the inputs is a logic 1 or is a logic true, then the output is a logic true. The output becomes a logic high if any one of the inputs is a logic high. So that means that with this kind of expression, the only time the output will have a logic 0 or a logic low or a logic false is if all the inputs are a logic false. So it is only in the first case that you find a false, because this is an OR gate. So everything, because as long as there is a true in the input, then the output is true. You only need one condition to be true, because the A is a condition, B is a condition. That's why when we are drawing our ladder diagram, we have, so here again, we have two inputs. I told you we normally use the normally open contacts. I'll tell you when we use the normally closed contacts. So if A or, this is now or, not and, or B, sorry, I didn't complete drawing it properly, or B then Y. Okay, if A or B, then Y, meaning that the output would be a logic 1 or a logic true if any of the inputs is a logic true. Now, please don't draw this. I'm just trying to illustrate this. Let's see if this works. If A or B. So let's say this is true. Let's start with the first one, false, false. If it works, we are checking whether this diagram works. So let's say we have a false here, and we have a false. The diagram says that, I mean, that our expression is if A or B, if any one of the inputs is a logic high, then the output is a logic high. Now, if you look at this expression, the way we have drawn this, so we have A as false. So you can assume if there was, we say that it is logic that flows in a ladder diagram, but you can think of it also in its analogy of an electric current passing through. But here we know it is logic. So if both are false, it means they'll remain open. And when they are open, then the output would be false. Okay? But if, let's say both are true, let's use both are true, then the A will allow logic, B allows logic, and then this is true. Okay, so far so good. Let's say the first one is false. The second one is true. So it means the first one would, because if it is false, it means it is not activated. That's what we mean. It's logic 0. And if it's logic 0, it remains open. Then the second one is closed, meaning the second one turns green. So we can see that there's a problem, because if the logic expression requires that because we already have a true in the input, the output is expected to be true. But logically, if we look at our diagram, if this is false, meaning it is not activated, and this is true, which means it is activated, then we can see that this is going to remain open. If it remains open, it is not going to allow logic to pass through. And therefore, we cannot use this ladder diagram to represent the OR function, because it will work for the false, false, it will work for the true, true, but it will not work for the false, true case, because one of the gates would still be false and the other one would be true. So because one will be open, the other one is closed, then we still don't have logic passing all the way through, because remember we said that the normally open contact works in a way that when it is false or when it is open, it does not allow logic to pass through. But when it is activated, when it is closed, then it allows logic to pass through. It's like a gate where a valve. So if the valve is open, it doesn't allow the logic to pass through. If the valve is closed, then now it allows logic. In that case, maybe even if it's water or whatever. So normally open means the valve is always left open, meaning there's no way water will pass through. But when it is closed, then now it directs water. So now let's see, for example, another diagram. So this cannot work. So we have to modify the diagram so that the OR function can work. So how do we modify the diagram? That's what we want to do. Let's see if this one will work. Because we know the first instruction is if, so that you check the states of the inputs. So you have input A. So if A, but now we want B. So remember we connected them here in series. That's why it didn't work. Let's try and connect them in parallel and see if it works. So in parallel means, in parallel means we can now have this going there like that. And then we can pick up this from here. And we draw another one there. And then now, like that. So that now we have our input B here. And therefore, the OR function is in between. Okay? If A or B, then. So this is where we have the logic expression. Then now we have our output. So now from here, we can actually see that let's take the state 0, 0. Okay, or false, false. So if we take the state 0, 0, then we know if 0 or 0, then we'll have an output of 0. Okay, now if we change one of them to 1, let's say this is where we had a problem. If 0 or 1, so that means the logic can either go through A or go through B. If it goes through A, it finds that A is logic 0, meaning it is open, so logic cannot pass through. But then it can also pass through B, which is a logic 1. So B is activated, so logic can pass through. So logic can either pass through A, which in this case it cannot because of logic 0, or it passes through B. And therefore, it changes the state of the output, and the output can now be logic 1. The same way, even if we inverted this so that now this is logic 1, and then now this is logic 0, we can see that still it works because logic can now go through A because A is the one that's activated. B is still open, and so logic cannot go through. But logic will still get to the output because A is activated. Okay, and of course 1, 1 means it can go through any one of them. It can either go through A or through B because both would be activated. And so this is the ladder diagram that represents the OR logic function. This is what represents the OR logic function. So notice it's simply connecting the two inputs, the normally open contacts, in a parallel format. Okay, so that is our logic expression for that. I'll give you certain notes at the end of this class because now they are ready. That has some of more information regarding some of these diagrams. Now, how about the NOT gate? So we've done the OR, the AND. So how about the NOT gate? The ladder logic NOT function. Keep calling them the NOT gates, but NOT gates is suitable for digital electronics. It's a terminology for digital electronics. Now, the NOT function basically is the only function that always has a single input and a single, of course, the output is single, but the input is always single. The other functions usually have more than one input, sorry. But for this, the NOT function, or for those who remember third year digital electronics, the NOT gate has a single input. Okay. Now the NOT gate, or the NOT function in this case, is always implemented in using a normally closed contact, and then you put a relay or the output coil. okay? And you connect both of them in series. So to represent a NOT gate, we know that we usually have an input and an output. The NOT function is simple. And so it's always having a true or a false. Okay. Let me just use that. And remember, it is a NOT function. So it negates. So whatever you find at the input, the output is negated. So if the input is 0, then the output is 1. If the input is 1, then the output is 0. Again, we can use the terminologies of false, true, high, low, and so on. But I think now it makes sense. So that when we draw the ladder diagram, we have agreed that to draw the ladder diagram, we need to use a normally closed contact like that. And then you still connect it to a coil on your output. Okay? So that you have your input A and your output Y. So for this, it means that, remember, the function of the normally closed contact is such that when it is not activated in its normal operation, it is allowing logic to pass through. But the moment you activate it, the moment you switch it on, then it opens, and then therefore it blocks logic from passing through. So in its normal state, it is always allowing. That's why we say it's normally closed contact, meaning in its normal operation, it allows logic to pass through it. But when you activate it, when you make it a logic 1 or a logic high, then it now closes. Sorry, it opens, because it's a normally closed contact. It opens, and therefore it blocks logic from passing through. So therefore it means in this state already it is passing logic. But when we activate it, then it will now it will block the logic from passing through. That's why we refer to it as a NOT gate. Okay. So every time we want to negate any expression in our design, or when we're using ladder diagrams, we use the normally closed contact. It's a very, very simple, but a very important function that we use. Okay. So again, I hope that would be clear. So we can do this for several other gates, okay? I will, because of time, I may not do all of them, but you have to be very careful, because remember, don't just cram these things. It's important that you master the concept. Remember that for the AND gate, we were connecting the two inputs in series, and for the OR gate, we connect them in parallel. But think about it. The reason we draw this the way we draw is not because it's not a rule of thumb that if it's an OR gate, we have to put them in parallel, and if it's an AND gate, we have to put them in series. Things change. We draw these ladder diagrams based on the truth table. Based on the truth table. For example, let's look at a different truth table just to show you what I mean. We've seen how we draw an AND gate. So about the NAND gate, about let's draw the NAND gate. Ladder logic NAND gate. NAND function. Again, remember from the truth table, we always know, let's say the inputs, still using two inputs, A and B. Then we have the output, Y. So 0, 0, 0, 1, 1, 0, 1, 1. So this is a NAND gate. A NAND gate is a gate that negates the AND gate. So whatever output you had in the, remember, the AND gate was the AND gate. For the AND gate we had, I think I shouldn't be doing too much of this, but I just need people to understand. For the AND gate, we had everything here except this. But the NAND gate is now the opposite, meaning the NAND gate would be 1, 1, 1, 0, meaning the NAND gate works in such a way, or the expression for the NAND function is in such a way that it will allow logic to pass through for all states of the input, except when both inputs are a logic high. The NAND gate simply checks both inputs. If they're a logic high, then the next thing is it blocks logic from passing through if both inputs are a logic high. But for the rest of the cases, it allows logic to pass through. So if you want to implement this using a ladder diagram, you have to be very careful and see if the expressions work, because now we cannot just look at it. Let's say we have just decided to draw it rudimentarily. We've just decided to pick, because now we are told that if we want to negate, we use a NOT gate. So let's say we have tried to use a NOT gate here and see if it will work. Oh, sorry, we connect the output. So we have A, B, and Y. So let's say we've tried to use a NOT gate. Let's see if it's true. Remember, the NOT gate allows logic to pass through in its normal state. If it's activated, then logic is blocked. So let's start with the first case where we have 0, 0. Meaning it's allowing logic, and so the output would be a logic 1. Because if the state is 0, meaning it has not been activated, then it allows logic. If the state is 1, then it blocks logic. So let's go to the other state, 0, 1. So you can see in this case that the first one will allow logic, the second one will block logic. So if you think about it, the output will not have any logic in it, because the first one allows logic, the second one blocks the logic. So the output will read as 0. Remember, the output simply follows the state of the input. So it takes the state of the input nearest to it. So you can see here. So if it is 1, 0, for example, the first one will block logic. The second one will allow logic. Okay? Now, the third one, 1, 1, both will, in this case, because they are all activated, they will block logic. So you'll have a 0. But you can see that already we have a mistake here. So therefore, we cannot use, because we know that the AND gate was just connecting these two contacts in series, we cannot use this. This cannot be a NAND function. So for the NAND function, you will realize that for you to achieve the logic expression from the truth table, then you will have to redraw your ladder diagram, and you will see that for a NAND function, the ladder diagram will only work in this state. Okay? Such that now this is your B. So remember, think about it. If we have a logic 0 and a logic 0, meaning we have all of them are allowing logic, because when it's logic 0, then logic can pass through. I mean, if it's state 0, if it's state 1, then logic is blocked. So these ones will allow logic. And you see, it can either follow side A or B. So this one will be logic 1, definitely, for 0, 0. Because if it's allowing logic, then it can follow whichever direction. Okay? How about the other state, if it's 0, 1? 0, 1. So it means logic would be allowed through A, and it will be blocked through B. Okay? It will be blocked through B. But still, because logic is allowed through A, then the output would still be 1, because logic can follow that direction, even if the direction of B is blocked. Okay? So again, that should be clear that that now works. How about 1, 0? 1, 0 should work also, because it's simply changing the direction of flow of logic. And so we'll be having 1, sorry, we'll be having 1 flowing here, and we have 0 flowing there. So it means that now logic will be allowed towards the direction of B and not A, because A is now blocking because it's activated. So it's blocking logic. And so still, because B is allowing logic, the output will still be 1. And of course, the last one, you can see that the last one still makes sense where both states are 1, 1. Block logic, and therefore the output would be 0 because A is blocking, B is blocking. So the output becomes 0. So you can see that now for a NAND gate, we are now using the OR structure, which again might be, so you just don't cram. Please understand the concept before you draw the ladder diagram, okay? And you will see if you do a NOR gate would now be the opposite of what we drew previously. So I will not do all of them for you, ladies and gentlemen. I will do the XOR gate because that usually confuses students a bit, but let me do the XOR gate and then I move on. I'll hope that you will read the notes and also do the NOR gate. So XOR. I want to do the XOR. The XOR function. The XOR function. Again, the best way to draw this is to come up with the truth table. And we all know the truth table for the XOR function. If we still don't know, then we'll have to go back and check how the XOR function behaves. So we have an output, Y. If we remember the XOR function, the truth table. For those who remember from third year, I also still remember that the XOR gate is a very unique gate, such a way that it only produces a logic 1 at the output when both inputs are of the opposite states. If the inputs are of the same state, then it provides a logic 0. But if the inputs are of opposite states, then it provides a logic 1. So in this case, 0, 0, because those inputs are of the same state, it's 0. 0, 1, because both inputs are of opposite states, you get a 1, then you get a 1 there, and you get a 0. I hope I'm correct. If I'm wrong, please remind me. Third year is a long time ago. I might have forgotten. I hope that's usually I think this is usually the state for the XOR, that it only produces a logic 1 if the inputs are of the opposite states. If the inputs are of the same state, then it will provide a logic 0. Let's see. Meaning, if you look at this carefully, it means that we'll need both the normally open contact and the normally closed contact, because we'll be having cases where you want one is state 0, the other one is state 1. So that means you have to negate the one of state 0, and then you get your state 1. Okay, let's see if we can draw this. Let's see if this is possible. All right. Drawing the ladder diagram for an XOR gate. So let's say the input A so we'll have A there. Then we have another input B. We'll need an input B. Let me start drawing it like that and see. A and B. But of course, we'll need an output. I'm not saying this is the final diagram. We have to reason our way through. So this is the output Y. So in one case, 0, 0 should give us a 0. 0, 0 should give us a 0. 0, 1 should give us a 1. 1, 0 should also give us a 1. So it means, therefore, ladies and gentlemen, you'll see that there is a case where we have A as logic 0, but we also have cases where there is A as logic 1. There are cases where we have B as logic 0. Then there are cases where B is logic 1. So the best way to have each, because now, unlike the other functions where the output it requires only one condition. For example, for the NAND gate, you see that the condition for logic 1 is that any one of the inputs is a logic 1. If the inputs are all logic high, then you get 0. That's one condition. Even for the other condition, again, the AND gate, for example, you only require, the AND gate condition is that if both inputs are a logic 1, then the output is logic 1. So you mean if you implement that if both inputs are logic 1, the output is logic 1, the other states are implemented from this expression that if both inputs, so meaning you only get an output of 1 if both inputs are logic 1. So the other states are 0. So even if you're programming this, for example, in C++, you'll be using the if loop. So if A is this equivalent 1 and B is equivalent 1, then output is 1. So the other conditions of 0, 0, 0, 1, 1, 0 will automatically be considered logic 0 because you'll write else. So everything else would be 0, okay? So but for the XOR gate, it is unique such that you cannot do that because it's like the expression for each line is unique. That is, the condition for 0, 0 can be 0. The condition for 1, 1. So you can notice if both inputs are 0, you still get a 0 at the output. If both inputs are 1, you still get a 0. Okay? If any one of the inputs is high, then the output is high, or if the inputs are of the opposite states. So now it therefore means that we have to specify each of the input conditions in our ladder diagram. Each of the input conditions. The other cases, they were falling in place easily, but here, each of the input conditions are important. So therefore, it means we'll have to draw another rung so that we have the opposite condition for the inputs. So we'll be having 0, 0, 0, 1. Yeah, okay. Let me just put it like this first. Let me see. The output is 1, so we cannot draw the rung with another output. The output is just 1, so we'll use it like that. So that you remember, I am desiring, again, I'm trying to explain this so that everybody gets it. Notice that this first condition here gives us a 0. The last condition also gives us a 0, meaning the outputs for this will be 0. So whenever you are writing a program, even if it's C++ or whatever, you consider the states that are active, then you conclude that else everything else would be 0. So you don't program your code for the outputs of 0. You program your code for the outputs of 1, meaning program your code to achieve a logic, the cases where you have a logic 1 at the output. Then you simply put a statement that that means that the rest of the other states will be considered 0. We are interested in having the output being 1. So it means that the alternative condition is the output being 0. So when we are writing our ladder diagram, when we are drawing our ladder diagram, we draw them with the condition of the output 1 in mind, just like we did with the previous cases. These conditions are the important ones. The other ones can be negated. I mean, the other condition for 0 could be the alternative condition. So you program your ladder diagram using this condition as the most important, the condition that gives you the output of 1. Therefore, once you program it that way, then it means that the other states, the other 3 states, are just the alternative condition, which is not important in this case. Okay, so we avoid writing conditions for 1 and then we write conditions for 0, 0, 0. No. We only write for the condition of 1, then we automatically negate, or we automatically use the other states as the alternative states. So it's like if A and B, then. So it means that the not cases, the negating cases, will be automatically considered in our logic expression. Okay? So it's like if I say today, if it is raining, wear a coat. You see, I have only mentioned about rain and the coat. If it is raining, wear a coat. But no, somebody would definitely understand from that statement that if it is not raining, then don't wear a coat. So the second statement is an alternative statement, but it is not important. It is not the subject of our discussion. We're just saying if it is raining, wear a coat. But that could mean that sometimes it's not raining and therefore I shouldn't wear a coat. So I cannot write if it is raining, wear a coat. If it is not raining, don't wear a coat. It means that would be a duplication. I hope that is clear. So in our endeavor to write ladder diagrams, we write ladder diagrams for the condition that the output is going to be 1. Then the rest of the other conditions are alternate conditions. If we program for them, then we'll be having duplicates. But remember, as engineers, whenever you're programming, you have to optimize your program or your code to ensure that it doesn't consume too much power. So therefore, you don't have too many lines of code. And so it becomes very simple. So in this case, our conditions of interest are these 2. So there is a case of 0, 1. And then there's a case of 1, 0 for A and B. So if A is 0, and I want B to be 1. So if I want B to be 1, meaning it is active, it's allowing logic to pass through, I can put it like that. Then the other one, A is 1, so I can leave it, yes, as a NOT gate. B is 0, so B is 0, I can leave it like that. When I say 0, it simply means if I look at this gate, I would automatically understand that if this is logic 0, then it is blocking logic. If it is logic 1, then it is allowing logic. But if this is 0, it is actually allowing logic. And if it is logic 1, it is blocking logic. Remember, they're operating in the opposite states or in the opposite logic. So let's see if this works. A is 0 and B is 1. Remember, these ones are still the same logic. This is still A, this is still A, and this is still B. Okay? So we are still having A, but now we have also negated it. Okay? We're still having B, but we have negated it. Okay? So let us see if this would work. So the condition where A is, let me look at the 2 conditions first. A is 0 and B is 1. So let's put that here. A is 0, B is 1. A is 0, B is 1. Let's see what the state would be like. If A is 0, then we know that this side is open. So logic is not passing through, definitely. That we know. So if B is 1, we also know that when you activate a normally closed contact, then no logic. So logic is blocked there also because it's logic 1. Okay? It's a normally closed contact. If it is logic 1, it means it's activated, so it's blocking logic. So it means there's no logic that can go through up there. But now, if this one we said was 0, so if this is 0, then it means logic is passing through. So logic is passing through there. And this is logic 1. So if logic 1 for a normally open contact, then logic is passing. So the first case of 0, 1, where A is 0 and B is 1, logic is passing. So this is going to be logic 1. How about the next case of 1, 0? The next case of 1, 0. So the next case of 1, 0, meaning that A is now 1 and B is 0. A is 1 and B is 0. Let's see if that works. A is now 1 and B is 0. So if A is 1, B is 0, it means therefore that not A would now, remember A we've said is 1, so the state is 1 and that is 0. So let's see how logic will be flowing here. A is 1, it's a normally open contact. So if you activate it, then what that means is that logic can pass. Okay? B is 0. So if B is 0, and this is a normally closed contact, logic can pass. A is 1, like we have said. This is a normally closed contact. So if you activate a normally closed contact, what happens? It blocks logic. And this is B is 0, and this is a normally open contact, so logic is blocked. So we can see that now logic is going to use the upper side, and still at the output we will get a logic 1. How about the case of 0, 0? Let's use the first case of 0, 0 and see if it works. The first case of 0, 0. That means both states initially are at 0, 0. Let's see what we get. So we get a 0 here. Both states are 0, 0. Let's see how this works. If this is 0, of course, it blocks. This is 0, pass. This is the one, the normally closed contact is 0. If it is 0, it means pass. The normally open contact is 0, it means block. So we can see that there's no output, because already there's a block in the first case, the upper side, then there's also a block in the lower side. So therefore, the logic will not pass through. Remember, we had agreed that logic flows from left to right, then top to bottom. Okay? Left to right, top to bottom. So if already from left, there's already a block, then there's no passing through. Okay, so even if B is allowed, that means even if the normally closed contact is allowing logic, but it's already blocked from the source, so it cannot pass through. So it means that this logic works, even if it was 1, 1, 1 for all the cases, which is the last state. Let's see if it's works when all the states are, or both states are logic 1. Let's see if that works. Both states are logic 1. Okay. Okay, so if both states are logic 1, then we are going to have, this is logic 1, this is logic 1, this is logic 1, and this is logic 1. So what does it mean? It means this is a normally open contact. If it's logic 1, logic passes. This is a normally closed contact. Logic 1, it blocks. Normally closed contact. Logic 1, it blocks. Normally open contact. Logic 1, it passes. So, but still, remember, there's a block there and there's a block here. So the output would be 0. So this is the expression or the ladder diagram that represents the XOR function. And as you will see, and probably you need to study, and maybe you have previously, the logic function, the XOR function, is a very, very important function that is used in a lot of applications in digital electronics. So we should be able to make use of it quite a number of times. I will give you certain examples later on once we are well conversant with this information that will teach you more or that will make use of the XOR function, and you will see how they are very, very important. Even in real life applications, we can make use of them. Okay, so basically what we are saying is you will be provided with a state, or you'll be provided with an expression or a logic expression, and then you are required to draw a ladder diagram. Okay, and that logic expression could even come from the gates themselves, because I told you these functions are just from gates. You have the AND gate, the OR gate, the XOR gate, and so on and so forth. So let me give you a practical example that you will find. Let me do another example, an example question that you will find. I'm drawing this from one of the past papers. I like solving the problems that exist in the past papers. The question is, write a PLC program to implement the combinational logic circuit shown. So you have a combinational logic circuit here, and it assumes you know these logic gates. If you have forgotten them, you'll have to go and remember. So here you're given a practical combinational logic circuit that consists of logic gates, and then you have been asked to come up with the appropriate ladder diagram that performs the function of this logic circuit. So that is the circuit. The inputs are A, B, C, D. The output, of course, is Y. So we are required to come up with a ladder diagram that performs the function of this combinational logic circuit. It's called combinational logic circuits, I hope you know by now, because it combines different logic gates into one in order to perform a certain function. So we have to determine what is that function. To know what that function is, we have to obtain the expression for the output. Okay, so to solve this, we have to obtain first of all the expression for the output in terms of the inputs and D. Yeah, that's the first thing we have to do, that we must first figure out what is the output in terms of the inputs, because it is through that we can now have a ladder diagram, or it is through that we can now obtain a logic expression. The ladder diagram can be too long because we have 4 inputs, and sometimes you might have 5 inputs. So it can be a very, very lengthy process. But if once you have done a lot of these examples, you'll realize that sometimes you don't have to draw the ladder diagram. But let's see if we can obtain the logic expression here, because the expression is all we need. That logic expression is what we use. If A and B, then Y, or if A, B, C, and D. So let's see. Because we have an OR gate, for those who have forgotten, this is an OR gate. This is a NOT gate. This is an OR gate. This is an AND gate. That's an AND gate. So our expression should be, here we have A plus B. Or in logic terms, we say A or B, but we know it's plus that we use to represent OR. So A or B. Here we have not C. We negate the C. So we have a negated C or D. So we can put that here, a negated C or D. A negated C or D. And then because the output is an AND gate, we can now have the output as Y. Now it makes sense. Y could be equal to A or B, and it's ANDed or it's multiplied with not C or D. Okay, so A plus B into not C plus D. Okay, so this is basically the logic expression that we have to come up with its ladder diagram. Now, I told you that the rule of thumb is always use the normally open contact. But in cases where you need to negate, you use the normally closed contact, because the normally closed contact, from what we have seen, is simply a NOT gate. So we use it to negate expressions. Now, it's very, very clear from observation, this to be very, very careful about this. If we were to implement A or B, then we note that they were going to be, it's like an OR gate. We have implemented an OR gate before. We were going to have an OR gate. So if I was to implement A or B, we were going to have something like this. So if I just speak and I don't do anything, somebody is going to cry foul. And by the way, ladies and gentlemen, let me do this. This, let me say this is A and B, is the same as somebody who does this. Again, the more you do this, is the more you will know. Otherwise, so let me combine this like this. So these two are the same. Even electrically, when you are doing your wiring, it's the same thing. Okay? So if you meet any of these drawings, you'll know that you're talking about the same thing. Okay? So let me redraw this again, because I was supposed to draw. I was just saying the implementation of A or B, we've done it before because it's an OR function. We've done it before, and we said that A or B can be implemented as this. So that this is A and this is B. Or you can tap it from here, it's the same thing. Okay? So remember, and then we put an output there. I'm not saying this is the diagram. I'm simply trying to illustrate how we can draw this. So basically, this is an expression for Y equals to A or B. Okay? So, but that's not exactly the representation that we're looking for. It's not the ladder diagram for this expression. Remember again, C or D have because it's an OR gate, could also just be represented as, again, I'm doing them individually. I'm not saying this is the solution. I'm trying to explain this so that we understand. It is not C. So we said whenever we want to negate, we use a normally closed contact. So we put this as C. So notice again, I've seen students make mistakes here. The expression is, the state is C, but the logic output is not C. So you don't put here not C. No. You don't label a normally closed contact when you have already put its expression as not C. No, you just leave it as C, but we'll know it means not C because it's a normally closed contact. So I've seen students before draw for me a NOT gate like this, and then they label it not A, which is wrong, because then it means you're double negating this. So please, when you say put this as not A, then it's like you're referring to as a normally closed contact. I mean, a normally open contact, which is not true. So you have to leave it as A, but you draw a NOT gate or a normally closed contact. Anyway, I digress. Let me go back to what I was saying. If we were to implement this individually, it's also an OR function. But we know that we are negating the C, and then we have a D here. So again, if we were to implement this individually, I'm trying to go step by step just for explanation purposes. This is not the solution. So here Y would be not C or D. So the reason why I've drawn these two is for you to sort of like just think and envision. And this is gained from your experience of interacting with ladder diagrams and as many as you can. Think about this. We are needing to draw Y equals to, so we can call this X and we can call this Y. No, because we have Y as an input, it will confuse you. Let me call this M and I call this N. So the real expression, the general expression is Y equals to M and N. But M, yo, N, yo. And we know that if I wanted to come up with this expression, M, N. So this is Y equals to M, N. So notice I've broken this down, and this is usually the best way to do it so that you understand the logic expression properly. I've broken this logic expression into the first part, A or B, the second part, which is C, not C, D, not C or D, okay? And then I know that my original expression or the general expression should be Y equals to, in this case, Mn. And logically, or using a ladder diagram, we usually have Mn in that order for an AND expression, because this means if M and N, then Y. So it's like saying here, the logic expression is if the logic expression is if A or B, okay? If A or B, sometimes I might ask you to write out the logic expression. So let me just write it properly. If A or B and not C or D, then Y. If A or B and not C or D, then Y. So you can see here that the main function here is what? Is the AND function. But now these are functions within a function, because now we have the A or B and we also have the not C or D. But the real expression, if read out through, is if A or B, which is in brackets, and not C or D, which is also in brackets, then Y. So the original expression is an AND expression. That's the overarching function. It's AND function. So what this therefore means is we can take these expressions and combine them to form the AND function. And that's what I want to do now, because that becomes the original, the real solution. So it means I have to combine this guy and this guy. The output is 1. So to combine them is easy. I take the first expression, A or B. So I can draw this. So this is A. This is A. This is B. Combine them. So that's the first part. Remember, our expression is if A or B and. So therefore, we know from our study previously that if it's an AND gate, you connect them in series. So A and B, we now want to combine them with C and D. So notice, again, I'm breaking this down so that it's very, very easy to remember. So I can draw it like that. Let me just draw it a long way fast, because students always have their way of forgetting this thing. So I need to remember this is the rail. So I cannot draw a rail here again. The ladder diagrams only have two rails, to the left and to the right. So we have to combine these two. So to combine these two, I have the node C, where you just write the C. And then again, somebody can say, you can tap from here and draw the D. Then, of course, you combine them, and then you draw the output Y, like that. So let me use a different marker to label this, so that we have, this is C, this is D, and this is Y. Okay. Now, you can see I have combined, so you have if A, so in between here is the OR. I mean, if A and this is AND, not OR, then you have C bar and D, then Y. Okay, then Y. So what this therefore means is that I didn't have to come up with the truth table, but I had to write the logic expression. The logic expression is very important. It's what will guide your ladder diagram. What does the expression say? And does it match up with the ladder diagram? So if A or B, so A or B is done, then we also have not C or D also on the other side. So the AND is in between, and then the then is here. Of course, it follows that the output would be obtained from the combination of AB and C bar or D. So it's a very simple thing to do, but you have to be very careful with and make sure that the logic expression is correct. Now, you might redraw this because, okay, this is another rail. Some students might just cram. I don't want anyone to cram. You might redraw this like this. It's still the same thing. Just like you do with your electric circuits. It's still the same thing as this. Okay, so that this is your A, this is your B, C, D, and Y. Okay, so you can see that here I just combine them because these are like, if we use the analogy of an electrical wire, these are wires. And so having these wires connected like this is the same as connecting them here like this. There's nothing that changes. Okay, nothing that changes. So as long as we know that OR means parallel combination, so this is also parallel combination, and means series combination. So we take a parallel combination and another parallel combination and we connect them in series. So we have OR and another OR, and then we AND them together. Okay, that's why it's important for you to understand AND, NOR, NAND, and OR. and the way they are drawn. Because once you understand that, then that knowledge will help you come up with these logic expressions. And then you can use them to draw your logic diagrams or your ladder diagrams properly. Okay, so there are so many examples also in the book, by the class book. Remember, we have a class book, the Programmable Logic Controllers by Frank Petruzella. So you can look at the worked out examples, and then at the end of each chapter, there are other questions or quiz that you need to attempt. They might not have their solutions, but if you are stuck somewhere, you ask me, I'll provide you with the solutions. I've tried to solve as many of those as possible. So try and solve that and obtain your solution. Okay. Now I want to move on to something else, ladies and gentlemen. So again, remember, we are still just trying to get the basics of ladder diagrams. The ladder diagrams that we are going to draw, especially when we reach the design level, are more of very complicated, not really complicated, but complex ladder diagrams. And so these are just the building blocks that we first need to understand. And then later on, once we go to the real design, then we'll probably understand how these building blocks are simply very easy to deal with. Okay. Now, I have another question here. Again, I've just seen it. I've just seen it in the past papers, and I wanted to solve it before I move on to the rules of a ladder diagram. Okay, I've just need another question here, and it might skip my mind in at a later time. So allow me to just indicate that it is another example. Okay, the question states that a process control, these are typical exam questions, a process control PLC ladder diagram okay, ladder logic diagram is shown below. I'll try and draw it quickly because of time. The ladder diagram is this. I'm doing it maybe prematurely, but it's because I don't want to forget. I might move on to something else and I'll forget it. It's not really prematurely. I'm sure we can still understand. A simple diagram, it's not complex. And we have here, I want to try and draw it as accurately as possible as I see it. I told you some of these drawings can be very difficult and complex when you're drawing them manually, but they shouldn't be a big problem. They should never be a problem, because after all, when we're dealing with PLCs, we don't have to draw them by hand. We always can drag and drop. That's all I always see, can drag and drop. Okay, but anyway, what I see here is I1, I2, I3, and this is very important. It's going to get into exactly what I wanted to talk about next. So this question is going to be very relevant. I2, I3, and now they've even labeled. This is very important. Let me just, O1, Okay. And out here we have another important diagram. Label them as this O1, and then this is M, this is OL, this is L2, this is L1. So we can call this is called a pressure switch. A pressure switch. I might not have enough space. The other one is a temperature switch. A temperature switch. That one is a motor starter coil. This is a manual push button. Manual push button. Okay. So I don't know, man. I've just tried to squeeze the diagram. I hope it might be small, but at least it's still visible. But this diagram is very important. It's very difficult to draw these diagrams because some of them are very detailed. But at least for our case here, that I can use this now to do certain illustrations, which are very, very important for us to understand. So now the questions were, because there are about 4 questions that follow this. The first question was, what do the individual symbols represent? What do the individual symbols represent? Then question number 2, what do the numbers represent? What do the numbers represent? Question number 3, what 2 conditions? What 2 conditions will provide a continuous path? What 2 conditions will provide a continuous path from left to right? From left to right, remember the scan cycle, across the run. Across the run. And then number 4, describe the sequence of operation. Describe the sequence of operation of the controller for 1 scan. That's 1 scan cycle, for 1 scan of the program. Good. So this is the diagram, and these are the questions that are provided. Very, very critical questions that could help us a lot as we study some of these things. So I just saw this and I figured, I cannot just ignore it. I probably just need to sort of quickly see if we can, at this point in time, be able to obtain solutions or figure out what the solutions are. But the real deal here is simply to look at the ladder diagram. It's a very simple ladder diagram, but it contains a lot of information. So that's why, again, this question is testing whether you know the components of a ladder diagram and some of the requirements which I'm yet to go to, but I think I've mentioned previously, and then be able to describe a ladder diagram and what it does by just looking at it. Okay, so you can see that the first question is simple. It's simply asking, what do the individual symbols represent? And it's a very simple but yet tricky question. If you tell me that the symbols represent, and this I can't remember because I've marked a lot of questions before, students are very interesting. So the questions here, I'll give you a sample answers that I've seen before. So the question is asking, what do the individual symbols represent? So one student would tell me that they'll draw for me and they'll say, okay, Mwalimu, you go sort yourself. That is a normally open contact. Then they look at the other one and then they see, okay, it's a coil. So then they'll draw for me again like this. And then they tell me that is a coil or it's an output. Okay, then they're done, which is wrong. We are not asking what those symbols are. We are asking what the symbols represent. That's a very, very deep question. What do they I know it's a normally open contact. I know it's a coil, but what do they represent? And that is what we have been talking about. So the best solution or the best answer to this question is, let me just put here solution. You could say that the individual symbols represent, not what they are, what they represent instructions. Now that's a good answer. Because if you remember, ladies and gentlemen, I was drawing ladder diagrams like this. Yeah, you can remember this clearly. And I was indicating some logic expressions that come with them. If, and, then. Okay? So you can see that I'm using terminologies. This logic expression becomes an instruction. So to PLCs, to all PLCs, whenever you put these symbols or you draw a ladder diagram, the processor will not look at them as normally open contacts and normally closed contacts. No, it will look at them as instructions. That's why in our expression of human beings, we were using logic expressions, if A or B, you know, that is how we understand it. But the processor for the PLC understands those as expressions of instructions. So it's like, go to this memory location, take the instruction you find there, execute it, and then update the output. And that's why our scan cycle is, you read, what are you reading? You're reading instructions. You execute, what are you executing? You're executing the expression from the instruction. And then what do you do at the output? You update what the state of the output is. Okay, so you read instructions, you execute that expression, and then you update the output. So the individual symbols here, I1, I2, I3, they represent instructions. They don't represent normally open contacts or normally closed contacts. They represent instructions. That's very important. Question number 2, what do the numbers represent? The numbers. So this was for part 1. So part 2, what do the numbers represent? So the numbers represent, this will come back to because it's very important, represent the instruction location addresses. So the numbers are basically addresses, because I told you that these are memory locations. I1 is a memory location. I2 is a memory location. I3 is a memory location. O1 is a memory location. That's why I was telling you that this part of the ladder diagram is a software part. There's nothing hardware about it. Because we are dealing with the processor and their memory locations, they're registers stored in there. So the instruction is go to memory location I1, pick the instruction that is there, then go to memory location I2, pick the instruction that is there, and then go to memory location I3, pick the instruction that is there, then execute them in the expression of the ladder diagram. You can see here you have I1 and I2 or I3, and then you provide the output. Because you can actually see here is you'll have I1 and I2 or I3. So I1 and I2 are combined together like that, or I3, then O1. Okay, so you have if, because it's an instruction. If I1 and I2 or I3, then O1. Okay, so if you wanted to write this, if is here, and then this is or. No, this is and, sorry. This is and. But this is or. Okay, then this is then. Makes sense. That's why I told you some of these ladder diagrams, you really need to remember the logic expression. The logic expression is what will tell you what the ladder diagram is all about. So now, I'm sorry it's so congested, but it's because I'm trying to explain a lot of things. So the numbers that I have in red, I1, I2, I3, are called addresses. We are going to go back to that later because there's also a whole topic on how to do the addresses. So different manufacturers or different PLC manufacturers have their own addressing systems, and you don't have to cram them. You can use the data sheet to tell you. So like this is a Siemens, or even if it's Allen Bradley, all their inputs are labeled I1, I2. So you'll move maybe up to I7. They usually go up to around I7. An 8-bit. So because you see you have 8 bits. So if you have an 8-bit system, you have to address them as I1. Some start from I0. Yeah, I think, yeah, some start from I0 to I7 or I1 to I8, so that you have an 8-bit representation. Then from there, the outputs are now O1, O2, maybe up to O8. So you can find that a manufacturer decides the first memory location is called O0. Then the last one is O7. Okay. Or you can start from O1. Now that's manufacturer specific, but we still understand what it means. Some use Q for the output. So the output, instead of O, it's Q1, Q2, Q3. So you see, it doesn't change anything because the principle of addressing is the same. So the I1, I2, I3, O1, those ones are, O stands for output. Other books will put them as Q. I stands for input. So some would not even say I1. Some can say I 0.000, then I 0.01. You see, I 0. So it's just the way the manufacturer decides to put the memory location. But what is important, what we have to understand, whichever nomenclature you decide to use, all we have to understand is that you have to provide the address for each of the inputs and the outputs. So that is a very critical part. You will see that all the ladder diagrams that are drawn properly have the addresses indicated in them, and those addresses are represented by the numbers. So the numbers we have here represent the memory locations, the addresses for each instruction, because we have agreed that whatever we provide here in terms of the symbols, they represent instructions, but those instructions are stored in a certain memory location. So the numbers represent the memory location of the instructions or the addresses of the instructions. I hope that is clear. So that was question number 2. What do the numbers represent? We have seen that the numbers represent the instruction location addresses. So where is the address for each of the instructions provided. Let me go to the third one, which is what two conditions will provide a continuous path from left to right. Sasa hii nataka wale wamesha soma kidogo wakaelewa. What two conditions will provide, you can look at the ladder diagram again. What two conditions will provide a continuous path from left to right across the rung? If you look at, or if you read the question again, you don't panic. You simply read and try to understand what it is asking. It's asking that there are certain two conditions. It's saying that there are certain two conditions. Those two conditions will provide a continuous path, meaning it will provide a logic 1 at the output. So there are two conditions that if executed, then there's going to be a logic 1 at the output, and that is what they are asking. What conditions will provide a continuous logic path from left to right across the rung? And the only way to do that is to understand the logic expression, the only way to know the solution. What two conditions? Very simple. Let us redraw this, but now without the many things, then we'll understand. So you can see that this is a very simple ladder diagram. It consists of this. Let me see how the other one is connected. Okay, it's connected before. So they're connected like this. Then you have your output. So the output is Y. This is what we have used before. Let's call it, so this was called I1, I2, and I3, because you have to refer to them like that. And this was O1. Okay. So what two conditions will provide a continuous logic path from left to right? Meaning, what two conditions will allow logic to get to the output O1? What two conditions? Now, if you think about it, we have actually indicated the logic expression and said if I1 and I2 or I3, then the output. So those are the conditions. So let's see the first one, the first condition. It means we are trying to look for the conditions that will have the output energized. We'll have the output have the logic 1. So let's look at the first condition. What is if I1 and I2, because remember this is an AND. Between I1 and I2, it's an AND function. And the only way an AND function, from the discussion we've had previously, the only way an AND function will allow the output to have a logic 1 is if both inputs are logic 1. So basically, it's a very simple question based on our study before, that for us to have an output of 1, then because we have an AND function, the inputs must both be of logic 1. So the first condition is if, so the first condition for the output to be logic 1 is if both I1 and I2 are activated. Because remember, they are normally open contacts. So if you activate them, they allow logic to pass through. So if you write if both I1 and I2 are activated, or I1 and I2 are a logic high, or true, I'll give you, that's still the same thing. Remember, I'm writing them in capital letters so that we differentiate them from our usual verbs that we use. So both I1 and I2 are activated, because if you have a logic 1 here and you have a logic 1 here, then it means that logic will be transferred to the output. But there are two conditions for a reason. There's the OR. meaning logic can either go through the upper rung or it can go through the lower rung. So the second condition, so if I1 and I2 are not high, we can still have the output as 1. How do we make the output as 1? If I3 is activated or closed, the same thing, okay, or logic high. So you can see that there are only two ways in which we can make the output go to logic 1. The first one is both the inputs I1 and I2 must be logic 1, or we have I3 being logic 1. So that was the question. And remember, it asked it in a very subtle way. What two conditions will provide a continuous path from left to right across the rung? The first condition is if you have I1 and I2 being activated, or alternatively, if you have I3 being activated. Those two will ensure that the output is a logic 1. The fourth question, which again now simply tests if you understand the whole operation, describe the sequence of operation of the controller for one scan of the program. Remember, I told you, ladies and gentlemen, in the previous class, that whenever you draw a ladder diagram, it is very important for you to provide comments. That's one of the conditions that I'm going to draw before we end the class today, that you must provide comments for your ladder diagram. And the comments are simply a description of the sequence of operation of your ladder diagram. So now, this is where you have to look at the ladder diagram in a holistic manner, okay? It's full of stuff. I've scattered a lot of stuff around it, but now I hope we can understand. Now remember, the ones that I have drawn in white, this basically from this point here to this point here is the program. It's the software between those two rails. That's the program, okay? But to the left, this part here is hardware, and this part here is hardware, which means these are physical switches. Remember, see how it's drawn nicely. The program is I1, okay? Let's look at the first normally open contact. It's I1. And our switch, the physical, what we were calling the field devices, is also labeled I1, meaning that now the PLC module, remember we were talking about the components of a PLC, and we said that there are input modules and then there are output modules. So the input module of the PLC is the one that is responsible for knowing that we have a physical switch here, I1. Its state should be transferred into the program as I1. So the memory address I1 should have the same contents as the state of the physical switch. And who determines that? The input module of the PLC. Remember, the architecture of the PLC had an input module and an output module. It's like a linkage between the physical device or the field device and the program itself. And they have the same label, meaning you have I1 as the memory address, I1 for the program, but it is also connected to the physical field device. So this pressure switch, so this simply means this is a pressure switch. This guy here is a pressure switch. I2 is a temperature switch. So the second one, so let me put it properly. Everything that I've drawn in green is a physical device to the left and to the right. So because this is labeled I1, this is the pressure switch we are referring to in the program. And this is the temperature switch that we are referring to in the program. And this is the I3. I3 is the manual push button. Is the manual push button that we are referring to in the program. So notice that the module is responsible for interlinking or connecting the physical field device with the program. Because here you'll have to press or you manually press a push button or you switch on the device, but that would be transferred into a logic in the equivalent normally open contact. So out here you have a switch that has been closed, for example. If you close the switch, that is transferred into a logic for I3. So it means you activate. So you have a logic 1 transferred to the to the program itself. So I hope that is clear. That's why I was telling you, you have to differentiate between the physical parts of the PLC and the program part or the software part of the PLC. The same way, let's say the output here is 1. What happens is the output module of the PLC will take that logic 1 and transfer it into a physical actuation. So you have what we call an actuator, so that the motor now is physically connected. And when it's, or electrically connected in that case, in this case, okay? When the motor is now electrically connected, what determines that is the logic of the output. So if the logic of the output is 1, we need to transfer that logic 1 into an electrical signal. We actuate it. That whatever converts it into electrical signal is the output module, because it will know that a logic 1 means we need to send an electrical signal to the motor. And then when the motor receives the electrical signal, of course, it will start rotating, or it will be activated and it will start running. And forget about, these are now physical devices. Actually, you can see the overload switch OL that's connected here is a physical device, usually for making sure that the motor does not run on excess current. So if the current is too much, then the switch, or you can use it to isolate the motor. Okay, so this part here is still a physical aspect. So please note that anything that I've drawn in green here are field devices. That's what we agreed we are calling them, field devices, because they're those devices that you can actually touch and operate. But whatever is inside the ladder diagram is a program that operates as a software. So I hope that is clear. So quickly, because of time, let me explain what happens to the ladder diagram. Then I give you the rules of our ladder diagram, and then we'll start other examples in the next class. So now I want to start. The question was, describe the sequence of operation of the controller for one scan of the program. The scan cycle, remember, says the scan cycle begins from left to right, top to bottom. That's one scan cycle. Then it repeats left to right, top to bottom. That's the second scan cycle, and it repeats like that. I told you each scan cycle will take less than a millisecond. It's very, very fast. So in this case, we can describe it as follows. So this is for number 4, to solve question number 4. What happens? You could say from the diagram here, you have a pressure switch. It's the first normally open contact. Then you have a temperature switch and you have a push button. So what does the processor do? Simply, a scan cycle is what the processor does from start to finish in one lap or in one iteration. So if you are a processor, the first thing that you will do is you will look at the pressure switch, the temperature switch, and the push button, because they are inputs. And so you have to take their status and then you have to record them into the memory. So the first thing is the state of the pressure switch, the temperature switch, and the push button. I'm just abbreviating them quickly. Push button inputs are examined, and the states of the push button, temperature switch, sorry, the pressure switch, temperature switch, and push button inputs are examined and recorded in the controller memory or the processor memory. Meaning, if you are the processor, the PLC processor, you will first run to the address of the push button and gain the address of the temperature switch, address of the pressure switch, and then look at the status of their inputs. What is the logic expression in those addresses? Then you put that in your memory. That's the first thing that you need to do. Once you have recorded in your memory the status of the push button logic, the status of the temperature switch and the pressure switch, then now you have to consider that if a closed contact is recorded in the memory, meaning closed contact means logic 1 and open contact, so let me just write that. A closed contact, meaning if you find that the contact has been closed there, you record it as, so it's recorded as logic 1, okay? And an open contact is recorded as logic 0, okay? So you are the processor. We are running as together. We want to see what happens. We've agreed that you first need to run to the inputs, check their status, then record that in your memory. How do you record them? If the contact is open, record it as a logic 0. If the contact is closed, then record it as a logic 1, okay? This is only applicable to this ladder diagram because this ladder diagram only has normally open contact. It doesn't have the normally closed contact. Then you now need to move on to the next part. And we understand now that an open or closed contact status is recorded as either logic 0 or a logic 1, okay? So now what happens is you have to check that when the states that you have recorded, the zeros and the ones for each of these, because remember the ladder diagram, it's replicated here. So maybe you went in and found that this one is 0 and this one is 1 and this one is 0, for example. Then now you look at the expression at the output. So what we can do, or what we can say about that, is that when the states of the input contacts provide a logic continuity, okay, then the output coil memory is given a logic 1. And let me just write that again. If, or maybe let me use the word when the states, the ones that you've recorded here, because we've said you go, if you find that it's a closed contact, that's a logic 1. This is how the processor thinks, okay? If it finds that it's an open contact, it records it as a logic 0. So when the states of the input contacts provide a logic continuity from left to right, across the rung, the output coil memory memory location or address is given a logic 1. Let me just say it's given a logic 1. Okay, And actually, when it's given, as soon as it's given a logic 1, let me just write this. This is now what happens in the physical world. As soon as it's given a logic 1, the output module interface, the output module interface contacts will close. That's what I told you. That as soon as we register a logic 1 here, what happens is, from the ladder diagram, as soon as you register a logic 1 at the output, then the output module, remember the PLC output module is an interface between the program and the physical devices, the field devices. So as soon as you record a logic 1 at the output, what happens is an electrical signal is sent to the motor, which actuates it, and therefore it starts running. Okay, that's what I've indicated here. That as when the output coil, based on the continuity from left to right, when the output coil is registered with a logic 1, then the output module interface contacts will close, meaning it will allow an electrical signal to go to the motor now and operate the motor. If it was a lamp, it will again now light the lamp. If it was a buzzer, the buzzer will go off. If it was a siren, the siren will go off, and stuff like that. So it doesn't have to be a motor only. The next thing that happens is we are simply trying to explain what happens to that circuit diagram. Okay. So the other part is when there is no logic continuity, when there is no logic continuity, I'm almost finishing. When there's no logic continuity, how do I put it? Of the program run, the output coil memory, location is set to logic 0, and as soon as it's set to logic 0, and the output module interface contacts will be open. So when the output interface the output module interface opens, then what happens is the motor is switched off. Okay, so that's, remember, this happens very fast. Okay, so to conclude what happens, we can say that the completion, okay, the completion of one cycle, of this sequence is called a scan. And remember, we know the scan is read, execute, and then update. So I need to write something about the updating, because we have read step 1. We read and we examined the pressure switch, the temperature switch, and the push button, and we took their statuses and recorded it in the memory. Then now, based on those states, we decided what was going to happen at the output. That is indicated there. That's the execute part. And then the update part, we can just write that the output memory location is updated during the scan. This is very important to remember. But the actual output, is not updated until the end of the program. Until the end of the program scan. What we mean is this, and this is very important. Let me use this simpler diagram to illustrate. We take the state of that, then we update the output. But that output is not, we just write the state of the output, okay? But we don't update it. It doesn't affect what happens here until we also go and check the one for this, because we'll have to, remember, we are running from left to right, top to bottom. So we'll go like that, then write the state. But we'll also have to come back and go through this and then write the state. So once we have completed the scan, this is when we now update the output status, and therefore it now affects what happens to the field device. So the field device is only actuated once a complete scan cycle is complete. I mean, it's done. Like that is once all the rungs have, because sometimes you can do the first run and then you have an output, but when you go to the second one, it changes what the output is. When you go to the third one, it changes what the output is. So it will keep changing the output status, but once the complete scan cycle is done, then now the output that you have there can now be updated. Updated means now you allow the output module to pick that status and actuate the field device based on the status that you have. So it is important for us to always remember that the output status, the update part of the scan cycle, does not happen up until all the rungs have been exhausted and all the states have been obtained. So the actual output is updated after all the scans are complete. That's when the field devices are actuated. So that's basically a simple illustration of what happens in that diagram. I think we've exhausted all the questions. I don't know whether there's another question remaining. No, describe the sequence. Okay, so that we have done. So ladies and gentlemen, that marks the end of our study today. I don't know if there are any questions, but that is the end of our study. Ochor, please ask. We have a few minutes remaining.
Yes, I'm currently in the library, but I've put the question in the chat.
You have the question in the chat. All right, let me see if it's possible for me to access the chat. What if for the NAND function, we used the AND function, cascading normally open contacts, and then cascaded it with a NOT function? Yes, that can work. You can always take, and basically you can do this even in digital electronics. You can take an AND function, then you cascade it with a NOT function. The problem is, and we must have been taught this in third year, when you use so many gates for only a simple expression, then you're spending more resources to achieve a very simple output. So we discourage the use of several functions or several gates when you can only use one. So if you buy a single NAND gate and it's 10 shillings, and then somebody else goes and buys an AND gate, which is 10 shillings, a NOT gate, which is 10 shillings, it means, yes, you will have achieved the same result, but you'd have used more resources because you've used two different gates. So the same way in PLCs, and that is part of what we'll discuss in the next class, it is important to make sure that your program is as optimized as possible, meaning use the least number of inputs and outputs as possible. So cascading can work, but only for certain specific functionalities that require that you must use such cascades. But there's no need of using an AND gate and a NOT function to achieve a NAND function. We only use that if, for example, if you go to the market and you don't find an AND gate, then you'll be forced to pick up an AND gate, you cascade it with a NOT gate. But if you can find an AND function, then use an AND function. So that goes into the optimal use of your resources. And it's one part of a big part of design. In design, you ensure you use the least amount of resources possible to achieve the output. Because overall, the cost of your product usually matters a lot in the market. So I hope that is clear. So principally, it can work, but you need to make sure that you optimize your work. All right. So I think that is done, and our time is up, and I have another class in 1 minute. So allow me, ladies and gentlemen, to leave. I think we'll meet again on Wednesday. So thank you very much for listening. Continue your studies and have a good day. Goodbye.